can't believe this. I've been studying this table for almost 3 hours and I still don't get it. I'm gonna bomb this test tomorrow.
Sam. Do not give up so soon. Quitting will get you nowhere, and besides, the periodic table is easier than you think.
Who are you and what are you doing here?
I came here to help you, Sam.
Help me? How can you help me? What do you know about the periodic table?
Well, Sam, I guess you could say I do know a little bit about the periodic table. Let me introduce myself. My name is Dmitry Mendeleev, but you can call me Dr. D.
Okay, Dr. D. Who are you and why are you bugging me?
Sam, I'm the scientist who created the periodic table. So I guess you could say I do know a little bit about it.
You created the periodic table? Wow. Oh, so I guess you're the reason I have this huge test tomorrow. You didn't have to complicate my life like this, you know.
I didn't complicate your life, Sam. Actually, I made it easier.
Easier? How do you figure?
It's so simple. All I did was take all the information that scientists have gathered over the years and classified it into an easy-to-use table. This table!
If it's so easy to understand, then how come I can't understand it? It seems so...
Complicated? Strange? Weird?
Yeah, weird.
It is not weird.
Well, if it's not weird, then help me. My test is tomorrow, and at the rate I'm going, I'll be up all night studying.
I thought that you would never ask. I'd be glad to help you. There are so many things I want to tell you about this table.
Like what?
Well, like how the table is arranged into periods and families, and how easy it is to read the information in each box. I would also like to tell you about my friends on the table. The metals, the transition metals, the non-metals, metalloids, halogens, noble gases, and rare earth metals. I can't wait! I'm so excited!
I see that. I never thought someone could get so excited over this table. It still looks hard to me.
Oh, the periodic table is a piece of cake. I'll prove it to you. So let's begin. All right, Sam. What is your favorite sport?
Well, track, of course. Couldn't you tell?
Oh, yes, I should have guessed. But tell me, Sam, what makes a good runner?
Well, someone who is athletic, of course.
Yes, athletic. Very good, Sam. Now, I want you to think of all the elements on this table as athletes.
Athletes? How do you figure?
You see these rows going across the periodic table, Sam? There are 7 rows of elements in the periodic table, which we like to call periods. The first element in the period is always the extremely active solid. Your true athlete.
Wow, so the first elements in the period are active solids. So what are the rest of them?
That's the interesting part, Sam. You see, the more you go to the right on the periodic table, they become less active. You have your outstanding athletes, your so-so athletes, and your never should play sports at all athlete.
Okay, I think I understand. Active solids always are at the beginning of the period. And as you move across the table, the elements get less active until you end up with an inactive gas.
Yes! Excellent, Sam! I knew you'd catch on quickly. Get it? Catch on quickly like you catch a baton in the track meet? Forget it.
Yeah, I get it. But what about these? Are they periods too?
Oh no, these are what we call families or groups.
Families or groups? What are they, like brothers and sisters?
Sort of. Watch closely. They'll explain it to you.
Oh, cool. How do you do that?
Secrets of the trade. Now pay attention.
Yeah. Pay attention, Sam.
Okay, sorry. Hey, do I know you?
Well, you better know me. You put me on your french fries all the time.
I do?
Yeah. Well, most people know me as Salt.
Oh, I thought I recognized you. You're salt. I mean, sodium. And yes, I won't ever eat my french fries without you. Hey, what are you doing here?
I came here to introduce you to my family and to explain why we're a family, and why all elements have families. They're not just here to keep each other company, you know.
So this is your family?
Yes, we're the alkali metals family. All the elements in family number 1, except for hydrogen, make up our family. I'll just let them introduce themselves to you.
Hi, Sam. Nice to meet you. I'm lithium. I'm the element responsible for the new high-powered lithium batteries, like the ones we have in this cellular phone.
Hey, I have a cellular phone just like that.
Yeah, you do, and I'm sure you'll thank me the next time your friends call you on it.
Yeah, I probably will. But I'm sure you didn't come here just to discuss batteries. There's still something else I need to know about you, isn't there?
Well, actually there is. As you can see, my symbol is Li, and my atomic number is 3.
What does that mean? The atomic number or whatever you just said.
Sam.
No, I know. Let me answer. Please, no.
It's
People,
so
people,
simple.
let me
It is
answer.
so simple.
People, I know
what
the
I'm
answer.
talking about.
Please,
I know.
The atomic number identifies the number of protons in the atom of an element. For example, my atomic number is 3, which means that I have 3 protons in my nucleus, 2 electrons in my first energy level, and 1 electron in my second energy level.
Wait a second. Refresh my memory. What are protons and electrons?
Protons are the positively charged subatomic particles found in the nucleus of an atom. Electrons are the negatively charged subatomic particles found in the energy levels outside the atom of an element. Kind of like the positive and the negative charges on a battery.
Oh, that's true. A battery does have a positive and negative charge. But I still don't understand what you mean.
Okay, Sam, watch closely. Protons, electrons, take your places. Okay, Sam, do you see the particles in the middle? Those are the positively charged protons. Now, look to the particles outside the protons. Those are the negatively charged electrons. Now you can see that the number of protons is equal to the number of electrons in a neutral atom. Do you get it now?
Yeah, I get it. The atomic number is the number of protons in an atom, and it's also the number of electrons in an atom. That makes sense. But how do you find the atomic number of each element?
Not to worry, Sam, dear. I'll help you. Besides, she is too annoying.
Who are you?
I'm Rubidium, but everybody calls me Ruby. You like my rubies? Let me show you how to correctly read the information that they put in each box about us. It's really not hard at all. Do you see the numbers at the top of each box?
Like this one.
Right here. No, this one.
No. Like these. These are the atomic numbers for each element.
Cool. Can 2 elements have the same atomic number?
Oh no, definitely no, Sam. No 2 elements can have the same atomic number. Each element is unique, like me. In fact, if you look at hydrogen, the atomic number is 1. Now look at helium, the atomic number is 2. Now look at beryllium and lithium. Their atomic number is 3 and 4. Are you starting to see the pattern, Sam?
Yeah. As you go from left to right across the table, the atomic numbers increase by 1. So in a sense, they're in order. Wow, I never noticed that before. That's really cool.
Yeah, you're right. It is pretty cool.
Yeah, well, what's the rest of the information in the box supposed to mean?
Hi, Sam. I'm Cesium. I'm going to let you know what the rest of the information in each box means. Can I, Ruby, please?
Cesium, you mean sneezium. She's got allergies, so we call her C's the Sneeze.
Bonjour, Francium.
Bonjour, mon ami.
Ruby, please let us help. Please, you never let us do anything.
Fine. You guys spoil all the fun. You're just jealous.
Yes, she's gone. She's probably going to polish her precious jewels.
I'm sorry, Sam, but Rubidium can be so possessive. She would have forgotten all about us if we hadn't interrupted. She's so caught up in herself and her rubies.
That's okay, but someone still needs to let me know what the information in the box means.
Do you see the symbol under the atomic number sign? Well, this is the chemical symbol for each element.
Yes, and just like the atomic number, each chemical symbol is different for each element. No 2 are alike. Just to make sure you don't get confused, the name of each element is under the chemical symbol. It's pretty simple, huh?
Cool. That is pretty simple. But what about the number below the element's name? What's that?
That's the atomic mass of the elements. Furthermore,
The atomic mass?
Yes, the atomic mass. The atomic mass is the average mass of all the isotopes of that element as they occur in nature.
I'm not sure I understand.
You see, Sam, any sample of an element as it occurs in nature contains a mixture of isotopes. Isotopes are atoms of the same element with the same number of protons, but a different number of neutrons. For example, here are 3 isotopes of hydrogen: protium, deuterium, and tritium. If you look closely, you will see that protium has 1 proton. Deuterium has 1 proton and 1 neutron, while tritium has 1 proton and 2 neutrons. As a result, the atomic mass is an average of all of these isotopes.
Okay, so it's an average of all the isotopes. That makes sense. But how come you guys are a family? You don't look alike and obviously don't have the same atomic number, chemical symbol, or atomic masses. So how can you be a family? Let me guess, you're a potato chip.
No, I'm potassium. My friends used to call me potassium potato, so I started eating potato chips. Now, I just can't get enough of them. So, I guess you're wondering why we're a family. Well, look at us. Look at us closely, Sam. What do you notice about us?
Well, all your atomic numbers are odd numbers.
Yes, that's correct, but not that kind of odd. We bond really easily with other elements and other substances. Yeah, we're real chummy. We just love to bond with other elements.
That's why I like to hang out with chlorine. When we bond, we form salt, and everyone loves us.
But sometimes you have to be careful, Sam, because we are the most active metals in the table with only 1 valence electron. We could be quite powerful when you combine us with other elements.
Yeah, like with oxygen and water. When you combine us with oxygen and water, the reaction can be pretty wild. In fact, when any of us combine with water, the results are hydrogen gas and heat.
Cool. Does that mean you could blow up or something?
Oh yes, definitely. Because of the heat produced, the hydrogen can begin to burn and may explode.
Quiz! Now let's take a quick breather. All right. Now let's check to see if you understand everything we've been telling you so far. You see, I'm going to ask you a question and give you 3 choices for answers, and you're going to pick the choice that best answers the question. Are you ready? Are you ready? All right, let's go. All right. Now, which of the following pieces of information cannot be found in the boxes of the elements on the periodic table? Is it A, atomic shape, B, atomic mass, or C, atomic number? Now take a second to think about it. My watch. Where's my watch? You think you have an answer? The atomic mass is located at the bottom of each box. The atomic number can be found at the top of each box. The correct answer is A. The atomic shape is not provided by the periodic table of elements. All right, guys. You think you got it? Well, great. Now let's go back and see what Sam's doing.
Okay, so all of the families share very similar characteristics. One key characteristic that I've learned is that families share the same number of valence electrons. So family 2 has 2 valence electrons, right? Thanks. But hey, where are you going? There's still a lot I don't understand. Oh, so Dr. D, does family 3 have 3 valence electrons and so on across the table?
Not quite, Sam. The number of valence electrons increased by 1 as you go across the table for families 1, 2, 13, 14, 15, 16, 17, and 18. But families 3 through 12, they're a little bit different. And we'll get back to them soon.
Oh, I get it. Like I know family 1 has 1 valence electron and family 2 has 2. So what you mean is family 13 has 3, 14 has 4, 15 has 5, 16 has 6, 17 has 7, and 18 has 8 valence electrons?
Exactly! You're learning quickly. Now would be a good time to review what you have learned so far.
Okay, well the first thing we learn is that the rows going across the table are called periods. Each period begins with an active solid, and as you move across the table, the elements get less active until you end up with an inactive gas at the end of the period.
Excellent! Keep going!
The next thing that we looked at were the families of elements. These families are groups of elements with similar characteristics and share the same number of valence electrons. And as you go across the table, the valence electrons increase by 1 for families 1, 2, 13, 14, 15, 16, 17, and 18.
You're brilliant, Sam! Don't stop!
And in here you have the atomic number of the element's chemical symbol, the element's name, and the atomic mass of the element. I've learned so much. Let's keep going.
Oh, not a problem. What's your next question?
What are these elements here in the middle? Are they a family too?
Well, why don't I have them explain it to you?
See what you've done? I don't understand why you insist on carrying that silverware around with you everywhere. Take me, for example. My pennies are in this bag, all nice and neat.
Well, look who's talking now.
Wow, let me guess. Silver, the silverware, right? Copper, the copper pennies. And gold, well, you've got lots of gold around your neck.
You guys give us away every time.
Don't listen to her. She can be so conceited at times. She thinks the whole table should revolve around her.
Enough bickering, you guys. We're here to help Sam, remember? Hi, Sam. Let's start by finding out first what you know about us.
Well, not much. Mostly just that you're located in the middle of the periodic table. I guess you're important, huh?
Yeah, we never get the credit we deserve.
Credit, get it?
You're right, Sam. We are important. We're located right in the middle of the table between families 2 and 13, and they call us the transition metals. We're constantly in transition because we don't know what we want to do in life. Like maybe I should become an astronaut, or a lawyer, or a doctor.
We're very much alike. That's why we're always placed together. But while we're similar, we're different from properties of other families. That's why we're never put with other elements in their families. I'm transitional too. Maybe I'll be a pilot.
So your characteristics are kind of alike, but in many ways you're unique, and you don't fit into the other families of elements. What about your valence electrons? Are they the same?
No. Metals can have 1, 2, 3, or even 4 valence electrons, but transition metals usually only have 1 or 2. When we combine with atoms, we can lose either one or both of our valence electrons. We can even lose an electron from our next to outermost energy level and share electrons when we form bonds with other atoms.
Yes, we are very generous elements. We're always giving away our electrons. That's why we can form so many different compounds. Hey, do you want an electron? Go ahead, take it.
See, we're very important and generous. If it wasn't for elements like iron, cobalt, nickel, and zinc, not to mention us, we wouldn't be able to build skyscrapers, have coins, or the indoor plumbing we all have, or, most importantly, the medicines that save lives.
Wow, I guess I never thought of all the benefits we get from elements.
I told you we never get the credit we deserve.
Credit, get it?
No, I guess you don't get the credit you deserve. But let me ask you this. Are all the elements on the table metals? That's all I've seen so far.
No, not all the elements are metals. That's a good question, Sam. You're really starting to get this, aren't you?
Yeah, it's starting to sink in now. But how am I supposed to tell which ones are metals and which ones aren't? And if they're not metals, then what are they?
Well, actually, Sam, we're going to be talking about 7 categories of elements today.
7?
Exactly. Why don't we start with the ones you're most familiar with? Metals. Did you know that of the 109 known elements, 88 are metal or metal-like elements?
88? 109 elements altogether? How am I supposed to find them all?
If you think 109 is a lot, then maybe I shouldn't tell you the table is growing. Scientists are discovering new elements.
Yeah, and they did make it pretty easy to find us. You see that big black bold line down the right-hand side of the table? Well, the 88 elements to the left of that are metals or metal-like elements. Do you know what properties make them metals?
What do you mean, like the fact that we use metals to make things like pots and pans?
Well, sort of. Let's look first at the physical properties of metals. What do you notice about these pennies?
Well, they're really shiny. They look brand new, actually.
Yes, they're very shiny. That's the first physical property of metals we're going to talk about. The shininess of the metal is called the luster. Because metals have luster, they're easy to identify when you see them.
Another property that we share is that we are all ductile.
Ductile? What does that mean? Do all the elements quack like ducks?
I will not tolerate him making fun of us like this.
Oh, lighten up. I thought it was funny. But seriously, ductile means that metal can be drawn into very thin wires. Like this. Give me back. Give me back. Do you see what I mean now?
Yeah, I see what you mean. I really see what you mean.
Next time I get to explain what ductile means.
Please ignore them. Let's try another term, Sam. Do you know what malleable means?
Malibu? Like Malibu, California? I've been there.
Not Malibu, malleable.
Oh, no, I don't know what malleable means.
Malleable means that metals can be hammered into thin sheets. Don't even think about it, you two. This is what malleable looks like. After the metal is flattened, it can be turned into various objects, like this beautiful gold jewelry.
So obviously metal can be heated.
Definitely. Most metals allow heat and electricity to flow through them easily.
Okay, but how come I never see the metal on my car heat up? All I see it do is rust.
I know, it's the worst. No matter how much you wash and clean your car, it still rusts.
Well, that's one of the only few flaws that we have. That's true. Do you know exactly why we rust, Sam?
Well, I thought it was mostly due to the fact that there's water and stuff on the cars from the roads.
Yeah, that's part of it. But actually what happens is a chemical reaction occurs on the metal, which causes the metal to corrode.
How is it a chemical reaction?
Well, do you remember when you were talking to the alkali metal family about valence electrons?
Yeah, those guys were way too funny.
Yeah, they're real characters. But do you remember what they were talking about with valence electrons?
Well, I remember that valence electrons are the electrons in the outermost energy level, and they can be gained or lost when elements form bonds with other elements. But what does that have to do with why metals corrode or rust?
It has everything to do with it. Let's take a look at our proton and electron friends again.
Metals can have 1, 2, 3, or 4 valence electrons. But because the energy level is weak, we tend to lose our valence electrons when we combine chemically.
Because we tend to lose electrons, metals will bond or react chemically with water or other elements in the atmosphere. When metals do react chemically, the result is corrosion or rusting.
Wow, so that's why my car is rusting. I guess there's not much I can do about it then, huh?
Unfortunately not. But don't worry, we're pretty strong, so we won't rust overnight.
Quick quizzes. Hey there, guys and gals. Is everybody still with us? Okay, well, let's take a quick brain break. Okay. Now, you know how it works. Here comes the question, and you give the answer. Let's go! Physical properties of metals include A, flammability, B, luster, or C, bonding ability. Now take a second to think about it. Where's my watch? You guys have an answer? Flammability is a chemical property. Bonding occurs in a chemical reaction. It's not a physical property either. The answer is B. Luster is the shininess of a metal. It is a physical property. So did you guys get it right? Well, great, because we're moving on.
Hi, Sam.
Hi. Let me guess, you're carbon, you're nitrogen, and you're oxygen. I'm getting pretty good at this, huh? So I guess you're from this side of the line. I guess you're different from the others then, huh?
I guess in a way you could say that.
Yeah, we're different from all the other elements.
How?
We're different because we're non-metals.
Non-metals? What's a non-metal? It seems to me either you're a metal or you're not.
That's exactly what we are, not metals.
Okay, I give up. Tell me.
Well, as you now know from talking with our friends, silver, copper, and gold, metals are shiny, malleable, and ductile, right?
We're just the opposite. We're not shiny, malleable, or ductile. And as a matter of fact, we don't conduct heat or electricity well either. We're actually pretty dull, to tell you the truth, and harder to recognize than metals. We're just dull and boring guys, I guess.
Well, then what makes you important?
You need us in order to live.
How do you figure?
Take a deep breath, Sam. See? Without us, you wouldn't be able to breathe. I make up almost 78% of the Earth's atmosphere. And I'm an essential nutrient for plants. Without me, plants wouldn't grow.
And without me, your body wouldn't be able to break down carbohydrates to make energy.
So what about you, Mr. Carbon? Why are you important?
I'm a vital part of your body. Your body contains a wide variety of carbons, one of which is sugar. That's why I love candy.
Oh, I love candy too. But why do they call you non-metals?
Well, besides the fact that we are not shiny, ductile, or malleable, we tend to have more valence electrons than metals. Atoms of most nonmetals have 5, 6, 7, or 8 electrons in their outermost energy level. Atoms with 5, 6, or 7 valence electrons gain 3, 2, or 1 electron respectively when they combine chemically. So in short, nonmetals tend to gain valence electrons and metals tend to lose valence electrons. I wish I had a nickel for every valence electron I get.
But you said that some nonmetals have 8 valence electrons. If they have 8 valence electrons, then their outermost energy level is full. So how do they gain electrons?
Excellent question, Sam. One, of course, I would be most happy to answer for you. It's pretty simple. The elements whose atoms have 8 valence electrons tend to be non-reactive. Their energy levels are so full, so in turn, there's not much they can do.
So the elements in family 18 all have 8 valence electrons.
Not quite, Sam. Look closely at the atomic number for helium. What do you see?
Helium's atomic number is 2. Oh, so helium can't have 8 valence electrons when its atomic number is 2. It has 2 valence electrons.
Yes, that's right. Always remember to check the atomic number of the element when you're looking for the valence electrons. Helium is the only atom in family 18 that does not have 8 valence electrons.
Okay, so let me make sure I understand this. Most nonmetals have 5, 6, 7, or 8 valence electrons, are not ductile or malleable, and are dull in appearance.
Yes, and remember, we're located to the right of the zigzag line on the table. We're sort of right of center. Not necessarily politically, though.
So all of these elements are nonmetals, right?
No, not quite. Remember when Silver told you that there were 7 different classifications of elements on the table?
Yeah, we've talked about metals and nonmetals. What's next?
Well, they're a mixture between metals and nonmetals.
Oh, great.
It's not that bad, Sam. Remember the zigzag line? Well, the third classification of elements lie on both sides of this line. We refer to these elements as metalloids.
Hey, that sounds like the name of a cool rock and roll group.
I'll let you see for yourself.
Bye, Sam.
Bye, Sam.
Cool, you are a rock group.
Rap group, not rock group. Here, let me introduce you to the guys. This here is Boron. And don't do any moron jokes. He gets really upset about that, alright? And over here you got Silicon. He doesn't say too much. He's always sealing his mouth shut and everything else he can get his hands on. That's why he's always carrying his silicone with him. And I'm Tellurium. I'm actually the leader of this group because I'm always telling them how it is.
So you guys are the metalloids. What does that mean?
Hey fellas, I got an idea. Let's just do our song for him. That'll explain it to him. 1, 2, 3. We're the metalloids. We love to make lots of noise. Our appearance can be dull or shiny, but don't be fooled. We're not tiny. We're malleable and ductile. We're not afraid to go the extra mile. Our brothers and sisters include germanium,
arsenic, antimony,
polonium. That's the time. Just look for us on each side of the black zigzag line.
Not bad, but I think you have a ways to go before you hit platinum.
Hey, I hear someone say they want to hit platinum. Well, come on, let's go.
Who do you think you are, man?
Did you at least get the point, Sam? I mean, all that characteristics about metalloids and all?
Yeah, I think so. You're malleable and ductile like metals, but you can be either dull or shiny. You could look like metals or you could look like nonmetals. So actually, you share properties of both metals and nonmetals. So how can I tell you apart from metals and nonmetals?
Well, that's pretty much up to you, Sam.
Yeah, but you need to remember where we're located on the table. We're on either side of that black zigzag line. See? Here we are.
And trust me, we're not going anyplace.
Okay, that seems pretty simple. But what else should I know about the metalloids? Do you conduct heat or electricity?
Yes, as a matter of fact, we do.
Yeah, but we don't conduct heat and electricity as well as metals. But we do a lot better job at it than non-metals. You see what I mean?
Cool, I get it. Metalloids are elements that have properties of both metals and nonmetals. They can be either shiny or dull. They're malleable and ductile, and they conduct electricity and heat better than nonmetals. How did I do?
Very good, but where are we?
Located.
Oh, that's easy. You're located over here. See? On either side of the black line.
He's got it, man. That's pretty good, Sam.
Stay smart, all right?
Man.
Thanks, guys. But what's next? We've talked about metals and nonmetals and metalloids. I know we're not finished.
You're right, Sam. We're not finished.
Here's Quick Quiz. Hold up! Let's give your medulla oblongata a rest, huh? All right. I'm giving the questions and you're giving the answers. Let's go. Which element listed below is an example of a metalloid? A, phosphorus, B, tin, or C, germanium? Now take a second to think about it. Where's my watch? You guys have an answer? Phosphorus is a nonmetal. And answer B, tin is a metal. The answer is C, germanium is a metalloid. So how'd you guys do? Because that's all for me. So I want you guys to take care, stay smart. I love you.
I'd like to introduce you to...
What's that smell? It smells like chlorine. And it's making my eyes water.
I tell you, everywhere we go, someone always notices how bad you smell.
It's not my fault that I smell bad. Besides, if it worked for me, what would people use to clean their pools?
Sam, this is fluorine and chlorine. They're part of the halogen family.
Halogens, like us, belong to family 17.
Well, if you're in family 17, then you have 7 valence electrons, right?
Yep, that's right. Because we have 7 valence electrons and only need 1 valence electron to fill our outermost energy level, we're the most active nonmetals on the table.
That's why we react very easily with the alkali metals in family 1. They're always giving away an electron, and we're always taking them, see?
Yep, that's why my best friend is sodium. He gives me an electron when we bond, and the result is table salt.
Well, actually, when any halogen reacts with a metal, the ending result is a salt. I also get along well with sodium.
That'll teach her for trying to take away one of my friends. Serves her right.
I can't believe you would do that to someone in your own family.
Okay, before you guys get carried away, let me make sure I understand this. When a halogen combines with a metal, the result is a salt. Well, if that's true, then what kind of salt do you make?
When sodium and I react together, we form a salt that is used to fluoridate water and toothpaste. That's why I love brushing my teeth.
Fluoridated water? Toothpaste?
Yep, for strong teeth and gums.
Gosh, before today, I never knew how important the elements were.
Yes, we are important, and it is nice to be appreciated. So do you like my family, Sam?
Yes, of course I do. I think it's really cool how each element in your family has 7 valence electrons, and they form salts when they combine with a metal. I guess it goes back to that old saying, metals tend to lose electrons while nonmetals tend to gain electrons.
By golly, I think he's got it.
Well, my job here's done.
Yeah, this has really helped me, but I have a feeling that there's still a little bit more to come.
Just a few more things, Sam, and then we'll let you go.
Like what?
Well, first tell me what you remember about family 18.
Well, I know that they're all nonmetals, and they all have 8 valence electrons in their outermost energy level, except for helium, which only has 2 valence electrons. Oh yeah, and because most of the elements have 8 valence electrons, they don't gain electrons, and they don't combine with other elements. What else is there to learn?
Very good, but actually, there's a little bit more to know about them.
Like what?
Well, the first thing you should know is that we refer to them as noble gases.
The noble gases? What are they, like royalty or something?
Well, you can call them inert gases if you think that's better.
Yes, noble gases are also known as inert gases. We call them inert or noble gases because all of the elements in family 18, except for helium, have 8 valence electrons and do not readily form compounds with any other element.
So all the elements in this family are gases?
Exactly.
You might even recognize some of them. For example, the gas in this inner tube.
I know. It's helium. My friends and I used to play with balloons filled with helium all the time. Of course, we're too old for that kind of stuff now.
Yeah, of course you are. And you're right, helium is used to fill balloons to make them float. I'm sure you'll recognize this one too, Sam.
What, that red neon sign?
Yes, neon gas produces the red color seen here in neon signs. Argon and several of the other noble gases help produce colors other than red to make up neon signs.
Cool. I've always wanted one of those in my bedroom.
Sorry, we can't help you with that one. Hopefully, we did help you understand the noble gases a little bit better.
Oh, definitely. The noble gases are found in family 18 and are called the noble gases or inert gases because all of them, except for helium, have 8 valence electrons, and they do not form compounds with other elements. And they're all in the form of a gas.
Excellent, Sam! Wouldn't you agree, Dr. D?
Oh, yes, he's been an A student.
Hey, I was wondering where you were.
Oh, don't worry, Sam. I'll never wander too far away. So how have you enjoyed yourself so far?
It's been great. I think we've covered most of the table, but I know we haven't talked about these elements yet.
You're right. We haven't talked about these elements yet. Do you remember when I said that there are 7 different kinds of elements on the table, Sam?
Yeah, we've talked about metals, nonmetals, transition metals, metalloids, halogens, and the noble gases. So these elements down here at the bottom are the only ones left. Don't they fit into a family?
Excellent question! These elements are called the rare earth metals. They share similar properties, so in a sense, they are a family.
But why do they put them down here at the bottom of the table, away from the other elements?
We put them down there just to make the table easier to read. That's it. No big scientific theory behind that one.
But are they dangerous or something? I mean, rare earth metals. Sounds pretty weird to me.
Well, let's take a closer look at them. The first row of elements is called the lanthanoid series.
The Lantha what series?
The lanthanoid series, a series made up of soft, malleable metals that have a high luster and are good conductors of heat and electricity.
Okay, so they are metals, but what are they used for?
Companies combine these elements with other metal or non-metal elements to make various alloys and high-quality glass, like the glass that I'm holding. Whoops!
Cool, but is the second row the same?
No. These elements are a little bit more powerful.
A little bit more powerful? What do you mean, like they're radioactive or something?
Yes, that's exactly what I mean.
Dr. D, is that you in there?
Yes, it's me, Sam. This series of elements are called the actinoid series, and they are radioactive. That's why I'm wearing this suit. Oh, but don't let me scare you, Sam. Even though that they're radioactive, they're not all dangerous. Take, for example, uranium. We use it to fuel our nuclear-powered electric generators.
Oh, so I guess we won't be using those elements in our lab class.
No, I would think not.
So let me make sure I understand this. The first row of elements is called the lanthanoid series and is made up of metals that are soft, malleable, and conduct heat and electricity.
Yes, continue!
And in the second row of elements is the actinoid series. They're also metals, but they're more powerful because they're radioactive.
Outstanding, Sam! But I better be careful, though. Soon you probably want my job.
Only if I could do the cool tricks that you do. Besides, you're the reason I've learned all this.
Well, I'm glad that I could have helped you, Sam. But maybe right now we should review what you have learned so far.
Well, where should I start?
At the beginning, of course.
Periods are the rows of elements going across the table. They begin with an active solid and end with an inactive gas. Families are the vertical columns on the table. They are grouped according to similar characteristics and share the same number of valence electrons. Atomic number. As you read the table from left to right, the atomic numbers increase by 1. Valence electrons increase by 1 for families 1, 2, 13, 14, 15, 16, 17, and 18. Reading the element boxes, the atomic number is displayed at the top of each element. It is followed by the element symbol, the element name, and the atomic mass. Metals are shiny, ductile, malleable elements that are very good conductors of electricity and heat. Most metals have 1, 2, 3, or 4 valence electrons and tend to lose valence electrons when they combine chemically. Nonmetals. They are located right of the zigzag line. They do not share metal characteristics. Most nonmetals have 5, 6, 7, or 8 valence electrons. They tend to gain electrons when they combine chemically. Metalloids. They are in between metals and nonmetals. They are malleable and ductile. They can be dull or shiny, and they are average conductors of electricity and heat. Metalloids. They are located on each side of the black line and includes the elements boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. Halogens. Most are active nonmetals. They have 7 valence electrons and only need 1 electron to fill their outermost energy level. They react easily with the alkali metals. Noble gases. They are located next to the halogens. They have 8 valence electrons and do not readily combine with other elements. Each element is a gas. Rare earth metals. They are located at the bottom of the table. The first row is the lanthanoid series. They are soft, malleable metals that have high luster and conductivity. The second row is the actinoid series. These elements are radioactive metals.
That was beautiful, Sam.
Thanks, Dr. D. You made learning the periodic table a lot easier and definitely a lot more fun.
Oh, the pleasure was all mine. But now, Sam, I really must go. Good luck on your test tomorrow, and remember, the periodic table is a piece of cake.